Hi Hudson. So I'd recorded a video of this in class today, but uh, the Mimi was acting up and there was some tech issues like I told you earlier. So I hope this one can help you understand what happened in class. So we were talking about these pages on the experimental design. I think it's 96 to 99 to 98. And in this experiment, I had what I brought to class was a meter stick. I tried to find a spring, but I couldn't find a spring. So Sanai was very kind to offer us a spring from his pen, which didn't really help. I also had a mass, a 500-gram mass, so I brought that with me. I'd asked someone to find a spring that we could use, but they couldn't. So in this experiment, the spring constant has already been determined by a previous experiment because they performed the experiment earlier. Now the students needed to put together an experiment to demonstrate that the conservation of mechanical energy, or they needed an experiment to demonstrate conservation of energy. They need to show that when all the mechanical energy of a system is initially in the form of elastic potential energy, then all of it is transformed into another form of energy. They're given a cart with bearings, negligible friction, a truck that exerts negligible friction, and a wooden block, and have access to other commonly available equipment in the lab. So this statement helps us because it means we can use equipment that's not stated here, or we can totally choose to ignore equipment that's stated here and then use other equipment that's commonly available in the lab. So part A wants us to draw a diagram of an experimental setup that could be used to show that conservation of mechanical energy, and give a list of equipment used, outline the procedure where the student could be able to take measurements to show the conservation of energy, specifically explain how proper procedure includes methods of reducing error. This is also important, and remember, every time you see reducing error, that's by taking multiple trials. Okay? So just keep that in mind. So this experiment, you have a spring. I told them in class that the spring could be set up two ways. It could be set up this way, in which case it will be compressed, right? If you put a mass next to it, and this track, you put the mass on a track and it has wheels, you could compress it if it's next to maybe the wall. You compress it and let it go on this frictionless track, and then all of this elastic potential energy, right, is going to be converted into kinetic energy. So since I know that this is true, this is expected to be true, elastic potential energy will be converted to kinetic energy because the cart and its mass will move in that direction. Then one of the ideas that I can have is to figure out the distance from where the distance to that compression up to like a certain distance, and I can try to figure out if I know this distance, I can try to figure out the time. I can record the time that it takes to cover that distance after it's let go, and when I record that time, I can use this distance and this time to find the velocity, because I know this is initial velocity here will be 0, the final velocity is what I want. So initial velocity is 0, final velocity is what I want. I know the distance is something, right? The distance, if it is known, I can set a known distance, so that's known, and I can measure the time. So already, since I have 3 quantities, kinematic quantities, I can find the fourth. So I can use this approach, and using this approach helps me to find the final the final velocity at this point, and then that final velocity, I can use this. I can say that elastic potential energy, which is half kx squared, is all converted to kinetic energy, which is half mv squared, and I can check whether I can do that for different compressions and then plot a graph. So this is one way I can set up my experiment to try and show that elastic potential energy is converted to kinetic energy. The only drawbacks of this setup is one, this velocity that I'll get here might most likely be an average velocity because this involves acceleration. It accelerates up to when it reaches a constant velocity. So I need to be careful to measure that constant final maximum velocity. The other thing is you could still have energy loss to friction. Even though they say it's a frictionless track, you'd still have some energy loss to friction. So this is one alternative. And if it makes sense, then you can go ahead and explain your experimental setup using this approach. The other approach that I suggested in class was you could have this spring on a level ground, right, on a surface, maybe a surface of a table, at which reference you consider your height to be 0. Then you set the spring facing vertically upwards. You place that known mass on the spring, and that will compress the spring by a certain amount, right? When it compresses by a certain amount, it's still not jumping off because you haven't yet pushed it to force it to jump off. Then you personally compress it lower, such that if you were to release it, it will shoot the mass upwards. So on the side, you would have a meter rule, right, stationed on the side, meter rule, and then you can measure, first of all, this compression, because you have two values. You have this position here, we call it position 1, then you have this position here, position 2. The difference between those two positions is your compression, right? So this compression is something you can change, and for each time you change each time you compress it, you let it go up, like you release it and it shoots upwards, the block will rise to some maximum height which you can measure, and we call that position 3. Just to note that this maximum height needs to be measured from this position, or this is 3. The maximum height needs to be measured from this, right? So it's the height from up there, so you need to clarify that in your procedure. That's the height that it's measured from. And so each time you change the compression, right, each time you change compression, because you're the one that's compressing it, you get a different height value, right? And those height values correspond to, each compression corresponds to elastic potential energy, and each height value corresponds to gravitational potential energy. So each time you can, and once you get the values of elastic potential energy and gravitational potential energy, you can sketch, or you can draw your graph of those two energies. You can draw your graph. We'll talk about the graph in a bit. So the guys in class chose to use this approach because it's straightforward. It doesn't involve having to figure out the distance or figure out the time and then use kinematics. It's straightforward. All you have to do is find the height to which it bounces, to which it's shot up, and then figure out the potential energy. So with that in mind, if you're going to use the vertical approach, and you don't have to, you can choose to use the kinetic approach. If you're going to use the potential energy approach, what do you need to measure? Well, first of all, you're measuring the height to which it's going, right? So that's one thing, and you measure the height using a meter stick. It's measured in meters. You're going to measure this compression, delta x, so that's also measured in meters using a meter stick. To calculate potential energy, that's mass times gravity times height. That means you need to measure the mass of this object, so that mass needs to be measured. So in this column of things to be measured, you would include mass of the object, which is in kilograms, because they told you to use the algebraic symbols for those quantities, and it doesn't have to say that it's measured using a meter stick, because some questions specify that you should tell what you're measuring with. The next thing that's going to be measured is the compression, right? The different compressions, they're measured in meters, they're measured using a meter stick. And the other thing that you will measure is the height to which it jumps. The units are meters, and it's also measured using a meter stick. So now the procedure has to be carefully written to reflect all of these things in your approach that I have talked about, things that are going to help you to come up with a graph of potential energy versus elastic elastic potential energy versus gravitational potential energy. So just some tips, and you're going to write this on your own and you'll submit it and I'll grade it. First of all, you can talk about how you can start by measuring the mass, right? You can start by measuring the mass. Then after measuring the mass, you can place the mass carefully on top of the spring, just like I showed you here, right? You place, because these are the steps you take. You place the mass carefully on top of the spring such that it naturally compresses it to some position. So you place the mass on top of the spring, on top of spring. Please be more detailed in your thing than I am. Just, yeah, on top of spring. After pressing the mass on top of the spring, you can record the position, right? You can record that position here, because this position will help you figure out what the compression is. So you can record that position on the meter stick, right? If you want to call it x naught, you can call it x naught. Then next thing you do is compress the block. Compress the block through a certain displacement x, right? After compressing it, record the new position of the block, the bottom of the block, call it x1, and again that's this position here, that's this position x1, right? So the compression will be the difference between position 0 and position 1, or x0 and x1. That will be your compression. After getting your compression, release the mass, right? Release the mass and it shoots upwards. When it shoots upwards, so you're releasing the mass from this position of x1. That needs to be clarified. Release the mass, it shoots upwards. When it shoots upwards, what happens is you are going to have a height. So you record the maximum height to which it reaches. Record the maximum height at which it reaches, and then find, make sure to record that height from position x1. So you have placed the mass, you've recorded the height. Since you want to reduce experimental error, you can, first of all, to create data points for the graph, you can repeat this, because I said earlier here that you're going to be plotting compression versus maximum height reached. Sorry. You're going to be plotting elastic potential energy, which is coming from compression, versus maximum height reached, which is the potential energy. So you're going to repeat this for different compressions, right? Delta x, and record the height h at each compression, right? You can repeat each measurement. Since if say you're going to have 5 compressions or 4 compressions, you can repeat each measurement 3 times at least and take average. This is important because they want you to show that you are reducing error. So you can repeat 3 times and take average to reduce error. And after you've repeated those many times and taken the average, you can calculate, this is still going, you can calculate the elastic potential energy using a half k extension squared, right? And then you can also calculate the gravitational potential energy using mgh. Then after doing that, you're going to plot a graph of elastic potential energy versus gravitational potential energy. Let me see what this says. Okay, maybe that's for this part. The other part was still procedure. So yeah, you can calculate the elastic potential energy using this formula, calculate the gravitational potential energy using this formula. This graph will come at the next stage. I was skipping ahead. And yeah, that's enough procedure. Your diagram setup is something that I drew here, this whole thing over here, where you have the springs showing the different things and the meter stick. If you're using the kinetic energy approach, then your diagram should reflect what's going on in that approach. So yeah, you draw the diagram here. Okay, so how do the measurements you've taken, how can they be used to determine whether energy was conserved? Be sure to state specific types of energy and the systems to which those types of energy belong. So first of all, you're going to plot a graph of elastic potential energy versus elastic potential energy from the spring, because it's coming from the system of the spring. So you can say earth spring system, versus the gravitational potential energy, that is earth ball system, right? That's earth ball system. So this is earth spring ball system, this is earth ball system. I mean mass, not ball. So when you plot this graph, because remember all of these quantities are determined from graphs, you can plot gravitational potential energy versus elastic potential energy, or you can do it the other way around, it doesn't matter. Elastic versus gravitational. What matters is that you're able to interpret this graph. What we know from this setup is that when elastic potential energy is maximum, so when this thing is at maximum compression, it doesn't have any potential energy because you haven't yet let it go. So that's why this will be 0. And then when elastic potential energy is at minimum, that means when the thing is fully stretched after shooting off the mass, like after it shoots off the mass, it goes back to this position after it's fully stretched, so then there's no mass. At that position, the potential energy will be maximum because the ball will have reached its highest point. So your graph will look something like this. Will look something like that. And we know that the slope of a graph will be change in the vertical quantity divided by change in the horizontal quantity. For these quantities to show that all the energy has been transferred, the slope of this graph has to be equal to 1. Slope of the graph has to be equal to 1, meaning, or explanation being that if the slope is equal to 1, then when I cross multiply these two things, if I cross multiply, I'll just have change in gravitational potential energy equals change in elastic potential energy, which shows me that they are equal, right? So my graph, the graph that I plot, you could plot gravitational versus elastic, or elastic versus gravitational. It will be the same thing. When elastic is maximum, gravitational is minimum. When gravitational is maximum, elastic is minimum. That slope must be equal to 1, and what that implies is that these two energies are the same. So energy has been transferred completely from one form to the other form. So yeah. Now part C, if the spring constant turns out to be larger than they initially measured it to be, how would that affect their results? So think of this. They have a spring, right? They measured the spring constant to be some value, K1, but it turns out that it's larger. Since it's larger, that means the spring is stiffer. Stiffer spring, right? Now, K2 is bigger than K1. What that means is that for the same force, the extension of the spring K1, right, will be, what do you think? You can pause and think and then listen. The extension in spring 1 for the same force will be greater, unless greater than the extension in spring 2 because the spring is stiffer. Since this extension is bigger than this extension, what do you think is going to happen to the elastic potential energy, which is half kx squared, right? For this spring, the smaller spring, elastic potential energy, since you have bigger extension, it will be bigger or greater than this one, since you have a smaller extension, right? This one will be a smaller elastic potential energy. However, and this is where this gets interesting, however, because this has a smaller force constant or a smaller spring constant, the force exerted, because remember force is equal to kx, the force exerted on the mass that is being shot up is going to be smaller because K1 is smaller than K2. The force exerted on the mass, right, is going to be smaller than the force exerted in this case, right? So in this case, this object will shoot up higher. The second height will be bigger than the first height, meaning that gravitational potential energy here will be bigger than gravitational potential energy here, right? So what does this mean practically? Think of it, if these equations are confusing you. A stiffer spring is harder to compress with the same force. Since it is harder to compress, the energy it provides to the system is lower. You will calculate a lower value for energy. When you calculate a lower value for energy, you expect the height that the ball is shot to be smaller. However, because the force is bigger, the height is going to be higher. So these guys will be confused. They'll be like, how come this spring that is giving us less elastic potential energy is giving us a higher gravitational potential energy? They will think that maybe there's some extra energy added to the system from an unknown force. So their results will be affected, and if you can explain this in words without having to use all of these symbols, because if I look at these symbols, I may not make sense out of them too much, but if you can put this in a paragraph, that would be awesome. So yeah, that's what we did in class today, and sorry this one came in too late. I'm going to okay, bye.